When discussing the Hausdorff dimension of product sets, I did mention that there do exist sets of zero-dimensional Hausdorff measure whose product nevertheless is one-dimensional. That theorem, at the time I wasn't sure where I had seen. Now it turns out it's in Falconer's book, The Geometry of Fractal Sets. Specifically, that is theorem 511 with a half-page proof. It's a bit stronger because you not only show that the product is of dimension 1, actually it has positive Hausdorff 1 measure. And the interesting thing about the proof in this book is that it's given as an alternative to the first examples of sets where dimension of A cross B is strictly bigger than dimension A plus dimension B. So this definitely is an example. The first examples of A and B for which this inequality occurs were given by Besicovitch and Moran. So let's write those names down. Of course, Besicovitch, the founding father of geometric measure theory. And this example was from 1945 in the same paper where they actually showed, so in that paper they showed that the dimension of A cross B is at least the sum of dimension A plus dimension B. And then they gave an example showing that it is strict. So the proof here given in Falconer's book, probably it's due to Falconer himself because he doesn't give a reference and says that this is a simple alternative to the example of Besicovitch and Moran. The proof does not use any machinery. It's A and B are constructed as subsets of 0, 1 consisting of numbers with certain zeros in their decimal place, which makes it really elegant. Given that earlier in that chapter he mentions that the proofs of the results, the earlier proofs of this dimension inequality from Besicovitch and Moran were rather technical and also imposed some restrictions on A and B. Not the proof of the counterexample, but in general the lower bound. We saw that Mattila's book that also gives a proof of this dimension lower bound used Frostman lemma and Frostman measures. So that's kind of a more modern approach which was discovered later than the work of Besicovitch and Moran. Again, in the nice historical remarks, which are very common throughout Falconer's book. That's one thing about this book that I love. It has a very specific and clear references to how things were proved, in what order, and where to find them. Of course, we have to also see what has happened since this book. But anyway, there he mentions that the treatment for this inequality that is given is due to Marstrand from 1954, which uses net measures, if you happen to know what they are. So that's yet another way of proving this lower bound. The ideas are very similar to the use of Frostman lemma, but per se, Frostman's lemma is not mentioned in Falconer's book prior to these proofs, only net measure. So if you want to find a different approach to proving dimension A cross B is at least dimension A plus dimension B, Falconer's book will be a place to look at. So the net measures are not actually difficult at all. Their definition is even simpler than that of Hausdorff measures themselves because it uses only dyadic cubes. Okay, so a little bit of history plus this amazing counterexample. Also in the proof, he mentions that A and B can be made into compact sets by addition of countable sets of points. So if you love to see that A and B are compact, that is also possible. So this is some follow-up to the video on this inequality, which I will, for your reference, put at the end of this video. So hope you find this useful, and see you in another maybe longer video.